And this is a picture of the setup being desiccated inside the desiccating setup. And what it does is that it removes the air inside, so it creates a vacuum to suck out all the air bubbles. Now, test 5, what my mentor did was reapply the second block, which is the second electrical plate. And if you take a look closely, you'll see that this is actually the top plate, and there's a bottom plate on the bottom too. And the PDMS is right between those two plates. And these are just really close-up looks of the setup. Results for test 1 and 2 is that they were both created on the electrical plates, but we basically achieved clear materials but low levels of transparency due to the milling tracks left on the Teflon block surface from machining. And what I mean by milling tracks left on the Teflon block surface from machining is that these Teflon blocks, when we're making the molding for it, it uses a milling machine where it grinds out a certain amount of material, and that tool actually leaves tracks inside. So you can see sort of like footprints, and that makes it very unclear. And we're trying to achieve something that's clear. Now test 3, where we tested the aluminum foil and the aluminum foil that was embedded between the PDMS. This was actually unsuccessful, but we found out that the materials actually, it can be removed from the PDMS. That means it's easily peeled off. However, the fact that it's trapped in between the PDMS film makes it very difficult to remove. Then we move on to test 4. And test 4 was very successful. We achieved a level of clarity and smoothness that was not available in test 1 or 2. And you can see from this image right here, the part where the tape cover is along the edge. However, the part that's exposed to only the aluminum foil is right here, and you can see the clarity in the middle. Test 5, the one with the second block, the top block, the electrical panel, we found inconsistencies due to bubble formation, and there are little bubbles everywhere. And we didn't know what it was, but we think that it came from the addition of the top block, because it was probably in the vacuum without the bubble being removed. So what it does is that even though it was in the vacuum, the top panel actually trapped air pockets in between, preventing these air bubbles from getting out. However, this test also showed us that it's actually a lot easier with the top panel to create a thinner material, and that can help us out later in later experiments. Observations. Test 1 and test 2, basically we found clear material, but it was not very transparent due to milling pattern footprint from the Teflon block that was mirrored onto the PDMS. Test 3, aluminum foil became embedded in the middle of the cured PDMS compound, making it impossible to remove, nor to use it as an electrical plate effectively. And test 4 was a success. The area exposed to aluminum foil is very transparent, and the rough edges of the PDMS can be trimmed. So that would leave us with the result of a completely clear piece of PDMS. Test 5, air pockets were formed in the bubbles that were not clearly cleared out in the vacuum, but we also discovered that we can also use that setup to create a thinner film. Now this is a comparison of the effect of aluminum foil plates. This image right here is the PDMS from test 1, and this is the one from PDMS test 2. They're both equally similar. And to visualize the transparency level, what I did was I put it above a coin and I took a picture. And you can see that the level of transparency is very low in test 1 and 2. However, with the application of aluminum foil that was actually airtight in test 4, we were able to completely see through and see even the details of the coin. And that was pretty impressive. So to look at test 4, which is the one with the clear PDMS, we viewed it under a microscope. And this is actually an image I took with my camera from the microscope lens. And this is right at the boundary between the clear part and the rough part of the PDMS from test 4. And these are, it just shows that the one with the parts exposed to the aluminum foil plates is a lot more clear and does not have as much inconsistencies as the ones exposed to only tape or just the Teflon block. In conclusion, it is pretty clear that the method by which test 4 was completed is effective and can produce satisfying results. Also, if this method is used, if it's used properly, it can prevent shorts between both electrical plates due to a constant distance determined by the depth of the mold, which is with Teflon block. However, I would like to complete more experiments so we can fully determine the effectiveness of this method and also to determine the minimum achievable distance between both electrical plates, so that way we can figure out how thin exactly we can get these PDMS films to be. Future studies include repeating test 4 as a method to generate consistent PDMS films for future experiments and applications. I would also like to decrease distance between the electrical plates without shorting, which is electrical plates touching each other during a charge of electrical current. And hopefully that would allow us to create thinner films. I would also like to get the chance due to, I didn't get a chance this summer because of lack of time and time constraints, but I would like to apply electrical charge and examine these particle patterns under the microscope. And finally, I would also like to use this method and set up to create and explore a new option in cadets, which is my co-mentor, in her study of dynamic tactile interfaces. These are my references. And I would like to thank Dr. Laura Kretschmar, Agatha Cadet, the lab workers, Laboratory for Nanoparticle Modification and Assembly, Department of Chemical Engineering at City College, New York, Dr. Sakai Acharya, Harlem Society, and all of HCS staff.
Why did you need the film to be transparent? To be
because, well, if you want to create this application was designed with one of the purposes in mind, such as to use it on an ATM. And the ATM, we want to be able to accommodate blind people and also people who aren't blind. So we want the material to be as clear as possible so people who aren't blind can still see the screen. And people who are blind can be able to feel the screen.
So,
there's also two doctor tests. One and two can be used for blind people, and you'll have the same results of success from blind people, but not people who can see, right?
Well, it wasn't only focused on this project alone, because what my role in this project is to develop a method that can create these films. And this project that I worked with under Agatha Cadet of the dynamic tactile interfaces is just one of the options that we can use these studies for. There are so many other applications such as contact lenses or even lenses for cameras, filters, many more applications like that. Any more questions?
What did you use for your hearing aid? What did you use for your hearing aid?
The hearing agent and the base were actually, I didn't make them, and we ordered them. And it's actually from a company called Silgard, and they specialize in making compounds like these. And we just used what they had and used that for our application studies.
What were your results for the third one, the third test?
Doesn't matter.
Third test was the third test was unsuccessful. The reason it was unsuccessful is because the PDMS leaked under the aluminum foil and caused it to lift up and become embedded in between the PDMS. Now, it worked, but it's just that aluminum foil was embedded in between it, and there's no way we can remove this aluminum foil without damaging the PDMS. So we considered it unsuccessful, but it was a good try. It was a good try. So we learned a lot from it.